Hey guys, Mr. Milton here. Today we're going to talk about chords and arcs. At the end of this video, you should be able to understand the relationship between chords, arcs, and central angles, and you should be able to find length and justify how you got them. Okay. A chord is a segment whose endpoints are on the circle. Okay. And a chord that passes through the center of a circle is called a diameter. So we're very familiar with diameters. Notice that is a line or segment whose endpoints are on the circle. So AB is the diameter here. Okay. Have a couple chord, or another chord here is PQ, endpoints on the circle. Okay. In this circle, a diameter is represented by AB, as we just talked about. And a radius is represented by PQ. Or sorry, not radius. Sorry, radius. We have one as OC here, and a chord is represented by PQ. Okay, obviously there are other radii here. AO is a radius. OB is a radius. So we should be able to identify diameter, chord, radius, those things. And now let's just run into our first theorem with chords. And within a circle or in congruent circles, congruent central angles have congruent arcs. Okay, we've already looked at that in our first section. Congruent arcs will have congruent chords. And then congruent chords will have congruent central angles. So it's the relationship between these three geometric figures, I guess, that are, I guess, in a relationship together. Central angles have congruent arcs have congruent chords. That means congruent chords will have congruent central angles. So in the diagram below, we have circle O is congruent to circle P. And they say, given that arc BC is congruent to arc DF, what can we conclude? So they're saying, hey, these two arcs are the same. BC is congruent to DF. Well, there's two things that we conclude based off of this theorem. First, we can conclude that their central angles have to be the same. So we can say that angle BOC in circle O should be congruent to angle DPF in circle P. Okay. We can also say, since these arcs are the same, that means that the chords have to be the same. So BC is congruent to DF. Okay. Another example down here, it says that it wants us to use the circle P to answer questions. It says what information is given. So what did they tell us at the beginning of this problem? Notice that we have these dashes here. Typically means that we have congruent length. That's what it means here. They told us here that arc QS is congruent to arc RT. You can tell that because they both have those dashes, that single dash. Okay, with this information, we can again refer back to our theorem and say that angle RPT, this angle that corresponds with this arc RT, should be congruent to angle QPS, this angle that corresponds with the arc QS. Okay. Now they're asking us about segment or chord QS. What do we know about chord QS? Well, chord QS has to be congruent to chord RT, or segment RT. Okay. So again, just a different way to look at that same theorem that we just talked about. The central angle is the same. The arcs are sorry, if the central angle is congruent, it's a better word. The arcs are congruent. The chords are congruent. All right, moving to the back, working on our second theorem, and that is within a circle or congruent circles, we can say that chords equidistant from the center are congruent. And congruent chords are equidistant from the center of the circle. Okay, so basically it's the same thing as the first statement, just the converse of it. Okay, and that makes sense in a circle where all the distance is evenly distributed. If it's the distance from the center of the circle will show how long the chord has to be. Okay. So using that information to answer these next couple questions, it says find the value of A and explain. Okay. So here we have a diagram where it tells us that PQ is 12.5, and then it gives us this dash here, and so we don't really have to think too much about it. It's 12.5 along with what they said. Now we're going to go back to our theorem, and our theorem says chords that are equidistant from the center are congruent. Well, this chord PR is 25. Okay, 12.5 plus 12.5. And it's 9 whatever units from the center, perpendicular distance. So our chord R, and I'll just name this S. Okay. Our chord RS is also 9 units from the center. Okay. And so since A is that value, that distance, it should be the same as PR. PR is 25, A must be 25. Okay. Again, our explanation more succinctly, PR and RS are equidistant from the center. Okay. All right, looking at that kind of the same way here. Notice that we're given this chord 36, and it is 16 units from the center. 18 plus 18 gives us 36. And on the other side, where we have our X, this chord is 36. Okay, since these two chords are the same, we know they must be equidistant from the center. So since this top chord was, or leftmost chord was 16 away from the center, then this rightmost chord must also be 16 away from the center. Okay, and that same explanation. The chords are equidistant, or the chords are congruent, so they must be equidistant from the center. Are equidistant from the center. Okay, and then our final theorem that we're going to work with today. Still dealing with chords. In a circle, a diameter that's perpendicular to a chord bisects the chord and its arcs. Okay. Theorem 4, in a circle, a diameter that bisects a chord is perpendicular to the chord. Okay, so basically the same thing as theorem 3, the converse of it. And then finally, in a circle, the perpendicular bisector of a chord contains the center. Perpendicular bisector of a chord contains the center bisector. Okay, so we'll use that in order to solve these next set of questions. So we want to solve for R, our radius. Here, notice that chord LM is has a perpendicular or Kn, I guess, is perpendicular to Lm. Okay? And so what that means is, since this is perpendicular to the chord, we know that it bisects the chord. So in this triangle, which I'm going to just redraw out here, in this triangle, we're still trying to find R. R is not disrupted or changed at all. Kn was 3, and Lm was 14, but we know that that was perpendicularly bisected. So this is 90 degrees, this is 7. And so now we can use Pythagorean's theorem in order to solve for R. And so I can say 7 squared plus 3 squared equals R squared. That'll be 49 plus 9 equals R squared. So R squared is 58. Okay. And so to find out R, I can take the square root of 58, and that gives me 7.6. Okay, and again, our explanation is that Kn is perpendicular to Lm, so it bisects Lm. Okay, and that helps us to set up that right triangle. Okay, number 2, looking at that, really almost the same type of problem. Here, notice that we're given this chord as 11 and 11, so the whole thing is 22, but we see that this chord is being bisected. So since the chord's being bisected, we know that this must be perpendicular to the chord. Okay, so again, a right triangle is made, or exposed. I guess we didn't really make it, we just discovered that it was there. Okay, we know that that's 11, and now we're trying to find y, which I called x because I'm used to it. Okay, and so now we can use Pythagorean's theorem again, and this time 15 will be by itself, and y will be on the side with 11, so y squared plus 11 squared is 225. Y squared plus 121, subtract from each side, and so we get 104. Y squared equals 104. And so to find the answer there, just making sure I didn't mess up, square root of 104 give us 10.19 or 10.2. Okay. Okay. Now finally, that third question, trying to find x, this chord x. Really the same type of problem, we're just moving where our variable is. It's perpendicular to this chord, so we know it cuts it in half. So this must be equal to this. We have a right triangle. We're going to use Pythagorean's theorem. 6.8 squared equals 4 squared plus, I don't know, I'm not going to call this x because it's not x, so I'll just say b squared for right now. Okay, I'll call this b because b plus b will give us x. Alright, so there we have it. So now we'll use our calculator, and 6.8 squared gives us 46.24 equals 16 plus b squared. Subtract 16 from both sides, and so I'll get 30.24 equals b squared. I'll take the square root of that. Square root of 30.24. Don't know I wrote 0.25. And that gives me b as 5.4999. Okay, so I'm just going to say, yeah, I'll just keep that for right now. Times 2, because that will give me this whole thing. And that gives me x to be 11.0. Okay. All right, so saw those and how the theorems worked in play with that. Finally, last question, it says, in number 3, find the distance from the midpoint of the chord to the midpoint of its minor arc. So again, a minor arc is just an arc that's less than 180. Okay, so midpoint of the chord, we're talking about this point here. They're asking us, what's this distance? And this seems to be a complicated question, like we'd have to do a lot more with triangles and stuff, but it really isn't. Notice here that we are given a radius. This radius is 6.8. That means we know the length of all the radii in a circle. The length of all the radii in a circle are 6.8. So this measurement 4 is actually part of a radius. From here to the circle is 6.8. From here to the midpoint is 4. So our equation really comes down to 6.8 minus 4 equals the distance from the midpoint to the midpoint of the minor arc. Sorry, the midpoint of the chord to the midpoint of the minor arc. So 6.8 minus 4 gives us 2.8. So not high-level math there, just understanding that this is a radius makes that a little bit simpler than maybe at first glance it seems to be. Okay, so there we have it. Using chords in a circle, looking at their bisectors, looking at their central angles, and their corresponding arcs, and then their distance from the center. Okay, see ya.